high-dimensional finite elements for elliptic problems with multiple scales.
Thank you. My talk now is work I did with Professor Schwab from the ETH. I was there to work with him for some time, and we have been working with each other since then. My talk is on a very well-known and basic equation, and I'm sure that you haven't seen it here a few times. A few of the talks here have mentioned it. So here you can see that on the left-hand side we have A epsilon, which depends on epsilon in that way. So you can see here that A epsilon x is A x and x by epsilon. So here I need to say that epsilon is very much less than 1. So you can see that A epsilon changes very fast from point to point. So it looks something like this. And here we assume that AXY now is Y periodic in Y, and by big Y here I mean the cube of size 1 in RD. So here we work in RD. This is very basic and well known. If you have read a book on homogenization, like the book, the well-known books by Ben Susom, Lioms, and Papanikolaou, Bakhvalov, and Panasenko, you can see that in order to find it, to solve it, to find U epsilon, we write it as a sum of, say, U naught x. Yes, so here first we assume that U naught also depends on x and x by epsilon. So we write U epsilon as an asymptotic expansion in terms of epsilon. So we write it as U epsilon as U naught x and x by epsilon, and then epsilon U1 x and x by epsilon. And if we want, we can write down a few more terms here, like epsilon squared times U2 x and x by epsilon, and so on. But all we need for now is U0 and U1. And I need to say, yeah, I should have said here, but I don't. So so we assume that Ui xy is Y periodic with respect to Y. Yeah, and so we have U0 as U0 xy and U1 as U1 xy and so on. But somehow we can show that U0 does not depend on Y. So it is Y, I just have U0 x. And it is also very well known that we can show that U epsilon here goes to U0 and epsilon goes to naught in the weak sense, in H1 naught. And if we have some regularity, we can also show a rate of convergence in H1. So it is C times epsilon to the 1/2. And here I have U epsilon minus U0 minus U, epsilon U1 x and x by epsilon. And I think that here we need to assume that U0 is in H2. So all we want to do is to find U0 and U1, as you have seen in a few talks here. And it is also very well known that U0 satisfies an equation, which is called the homogenized equation. And this A0 here can be found. And it is also well known that we can write U1 xy in terms of in terms of U0, and here is how we write U1 in terms of U0. It is sum and I goes from 1 to D of du. Where's U0? Here's U0 by dxi times wi xy, where wi xy satisfy an equation for y in terms of y inside the cube y. So if you solve this, we find wi, and then we put it, and then we solve this, we find U0, and then we put this and wi into here, we have A1. But then if we want to find Wi xy, we need to fix a lot of points, say x1, x2, and then we solve for each of them an equation in terms of y, so it is not simple to do. Now it turns out that we can find just one equation for both U0 and U1 at the same time, and it is the well-known two-scale homogenized equations, and it has been done, I think, in 1990 or 1991, 1992. So here we have an equation for both U0 and U1, and this holds for on phi naught inside h1 naught and phi 1 xy inside L2 h1y. So if this can be solved, we can have U0 and U1 at the same time, but it is in terms of x and y at the same time. So we need to solve an equation in R 2D, and it is not simple to do. So the aim of my talk here is to find a way to solve this, to find U0 and U1 at the same time. So at first we do exactly the same thing as when we solve a simple PDE. I should have a picture here, but I don't, so I make one now. So here assume that the domain is something like this. So when we want to solve a PDE, at first we divide it into a lot of cells, and the mesh size here at a level naught, say. So here is a level naught. The mesh size is h0 is say big O up 2 to the naught. And then inside each of these cells, we divide them into sub triangles. And here is level 1, and the mesh size at level 1 is big O up 2 to the minus 1. And then inside each of these triangles, we also divide them into sub triangles, and the mesh size here at level 2 is h2 of big O to the 2 to the minus 2, and at level L we have the mesh size as HL as big O of 2 to the minus L, and so on. So all of this is well known. And we define VL as the space of all the functions which are linear inside itself for level L. So we have V1 for level 1, V2 for level 2, and so on, and they are all inside H1 and inside L2. And it is fairly simple to see that V1 is inside V2 and so on. And since now we want to find U0 inside H1 naught, and we want to find U1 xy inside L2 H1y. So we define V0L as the intersection of VL and H1 naught. And it is V0L, and we also do exactly the same thing for the cube y. And well, when L is large, this is not what I want to say. What I want to say is the union of all VL is dense inside H1 naught, and VL naught is dense inside H1 naught, and VL is dense inside L2. And we want to find U1 inside L2. We want to find U1 xy inside L2 H1y. So we define, So we define V1L like that. So what I do mean here is V1L is the linear span of all the functions of the form say phi x times per psi y, by phi is inside VL, and per psi y is inside VL periodic. Yes. Oh, sorry. Yeah, I didn't notice that. So now we want to find U0 inside V0L and U1 inside V1L. And we solve exactly the two-scale homogeneous equation. Oh, somehow I lost it. Oh my God! Yeah, I just lost it somehow, and I can't find it. And so we just solve exactly that. But now we want to find U0L. So here we want to find U0L inside. We want to find U0L inside V0L, and we want to find U1L inside V1L, such that it holds for all phi naught L inside V0L and phi 1L inside V1L. And I think that it is well known how to do it, and we all know. So if we assume some regularity for U0 and U1, we can also find a rate of convergence. The rate of convergence for U0 and UL is, so U0L inside H1 and U1 minus U1L inside L2 H1Y. H1Y is just C times HL, where HL is the mesh size, and it is well known. But this V1L is extremely large. The V1L where we find U1L, U1 is extremely large. We can show that the dimension of V1L will be something like big O of 2 to big O of HL to the minus D. So it is something like big O of 2 to the minus 2D, since we solve it in both X and Y. So it is something like minus 2 to the minus 2 LD, which is extremely large, and L is large, so it is not simple to use the whole of V1L. So V1L is just VL10, so it's VL periodic. So you can see that it is not simple to use the whole of V1L to solve it. So the main point of my talk here is we are not going to use the whole of V1L, but we just use a subset of V1L. So let me just, oh yes, I have it here. Okay. So here is what we have just done. We solve exactly the two-scale homogeneous equation, but we find U1L inside V1L, and such that this holds for all phi 1 inside V1L, and with some regularity we can find a rate of convergence for U0L to U0 in the H1 norm and U1L to U1 in the L2 H1Y norm. And as I have just said, V1L is extremely large. The dimension of V1L is something like big O of 2 to the DL, so it's not simple to do. So now we are not going to use the whole of this V1L, but we just use a subset of V1L. So here is what we do. Let me recall that we have a sequence. So V1 is inside V2, so on inside VL, and they are all inside H1 and inside L2. For each of them, for each of VL, we define W0L at VL minus VL minus 1 in the L2 norm. So what it means is VL now is the direct sum of VL minus 1 and W0L, and we also do exactly that for VL periodic, and now we take the H1 norm. So we can write it as So we can write, say, VL as the direct sum of all those W0L and VL periodic as the direct sum of W1L. So it is why we can write V1L in terms of those W0L and W1L, and it is the direct sum of W0L0 and W1L1, where we take L0 and L1 from 0 to L. So here's the main point. We are not going to use the whole of this sum, but we just use those L0 and L1 whose sum is not bigger than L. So we just take a few terms here such that the sum of L0 and L1 is just not bigger than L. And we call it V1L. Now it solves exactly the two-scale homogenized equation. But here we want to find U1L inside V1L bar, such that this holds for all phi 1 inside V1L bar. And if we assume some regularity for U0 and U1, we can also find a rate of convergence. And the rate of convergence now is C times L to the 1/2 times the mesh size. And it is something like C times L to the 1/2 times 2 to the minus L. And if we compare to what we had when we used the whole of V1L, when we use the whole of this V1L, what we have is C times HL. So what we have here is not as good as what we have when we use the whole of V1L, but you can see that when L is large, this is not so much worse. But this V1L bar is just a subset of V1L, and we can show that the dimension of this V1L bar is just big O of HL to the minus D times L, which is much less than what we have for V1L, which is big O of HL to the minus 2DL. And I think that when we solve a PDE in RD, what we have is big O of HL to the minus D. So here it is just a few times more. So the main point of my talk is we do not want to use the whole of this V1L to find this U1, but we just use a subset of V1L, which I call V1L bar here. And the rate of convergence here is not as good, but it is not so much worse, but the dimension of V1L bar is much less than that for V1L. So we have U0 and U1. But what we really want to find is not U0 and U1, but we want to find U epsilon. So here is what we want to find. So how do we use the U0 and the U1 we have just found to find it? If you put U0 and U1 into here, what do we have? Say if we put U0 L into here, and we put epsilon times U1 L x and x by epsilon into here, what do we have? I can show that we do not have a bound in H1 for this, for the left-hand side. So if we put U0 L and U1 L, we just have none. So how do we use U0 and U1? We use what Sioranescu, Damlamium, and Jacques Carrizo called the inverse unfolding, which I defined it as the U epsilon phi here. So for each phi xy in L1 omega times y, we define U epsilon phi as a function in L1. So this U epsilon here is a map from from L1 omega times y, and you can write it as L2 if you like, to L1 omega. And if we use it for U1, then we have a rate of convergence for U epsilon, so it is a rate of convergence in H1. And it is in terms of epsilon and the mesh size. It is the sum of epsilon 2 and the 1/2 and the mesh size HL. And that is for the full tensor case. For the sparse case, what we have is C times epsilon to the 1/2 and L to the 1/2 HL, and we also use that U epsilon for U1L. But of course, we need some regularity for U0 and U1 here. If you do not have regularity for U0 and U1, then this will not hold. But if we do not have regularity for U0 and U1, we can show that when epsilon converges to naught, we can show that when epsilon converges to naught and when the mesh size converges to naught, this is what we have. So at least somehow we can find U epsilon from U0L and U1L. So I still have some time, right? Yeah. Yeah. So far, what we have is just A epsilon depends on x and x by epsilon. So what if we have x by epsilon square, so on x by epsilon n? So here, so say if A epsilon depends on, say, epsilon 1, epsilon 2, epsilon n, and yeah, so a simple example is just x by epsilon, x by epsilon square, x by epsilon n. Then we can do exactly the same thing. But now we need to find U0, not just U0 and U1, but we also need to find U2, U3, and UN, and so on. And we can use exactly the same way to solve this. And for the full tensor, we have the rate of convergence is the mesh size. But here we have big O of HL to the minus n plus 1 times D, which is very large. And for the sparse case, we have L to the 1/2 times HL, and here we have just L to the n times HL to the minus D. And we can use the same same technique to solve some non-linear equations, and it is what I am working on now. And we can also find the rate of convergence in terms of L. So here the norm is in W1P norm. So we have L to the power CL times HL. So when P is 2, here I have L to the 1/2. But when P is bigger than 2, then we have just have CL times HL. And a lot more has been done, but this is, I think, all I have time for now. Thank you.
Thank you. Other questions?
So the sparse grid works because your A is sufficiently smooth? What's the assumption of A here?
Oh, you mean that A, X, Y? No, we just need A bounded, and that's it. Yeah, we don't need A in C1, no.
Question away from me. So can you just clarify further, because it's kind of correlated. What is the minimum regularity required from A as a function of x and y?
You mean regularity for U0 or U1 or for A?
No, the original problem, A as a function
Oh, yes.
It is periodic with respect to y.
Yes, it is periodic with respect to y. Yeah, here I just need to assume that a x, y is inside L infinity. And apart from that, we just don't require any more regularity.
So L infinity on the product.
Yes, yes.
Okay, so
Looks smooth.
Yeah, I think that in the case of two scale, okay, I see what you mean now. Oh, all right, yes. So say assume that you have this, where is the two scale homogenized equation. Yes, I think I know what you mean now. Yeah, and so assume that we have this. So assume that here is what we want to solve. Then all I need is just a x, y is inside L infinity of omega times y. But for a epsilon, in order to get this, I think that we need to have a x, y is inside c omega L infinity y, or c y L infinity omega, and it is done in the paper by Ale, I think in 1992 or something. Yes, but if we just want to solve this for U0 and U1, here is all we need, and not any more than that. What's that? Sorry? Yes, if we want to use two scale conversions, when we say that U epsilon two scale conversions to U0 and U1, then in order to get this, we need a x, y is either c omega L infinity y, or a x, y is in c y L infinity omega.
Some of the comes, then you need to make it sure that you're correct with U1, right? Of x and y.
Yeah.
Like epsilon instead of y, right?
Yes.
Makes sense. Belongs to,
Yeah.
L2.
Mhm. Yeah. Yeah. Yeah.
So when you approximate compared to the small solution, it's a kind of post-processing process, and you need this defaulting operator.
Mm.
Can you comment a bit how numerically you do that?
We have not done it, but we don't think that it is hard, since what we need is we need to compute that U epsilon for E1. So where is that? Yeah, it should be somewhere. Okay. So here is what we need to find. But then you can see that U1L is now just piecewise linear. So I don't think that it is too hard to do, but we have not done it yet.
thank you once more.
Thank you.
We'll continue in half an hour.